Hi, I'm Tad Hunt, co-founder and CTO of Exablox. Today I'm going to talk to you about our OneBlox object store. This is the bottom layer of our technology stack. This is our layer that really handles object layout across consistent hashing rings, which is how we represent our clusters, as well as how the object database that is one-to-one with a storage device, like a drive, handles the objects that it's asked to store and retrieve and to iterate across. Some industry parallels to our type of technology is really the first generation of this stuff is all peer-to-peer consistent hashing and distributed hash tables. A lot like what you see in peer-to-peer like file sharing technologies like BitTorrent. We really got started back in around 2000 with this Cord stuff from MIT. And BitTorrent's one of the ones that have figured out how to make this work really, really well at super high scale with 50% of the nodes changing on a daily basis. So you imagine how well it works at internet scale. Think about in a data center or across a couple data centers, things are changing at a relatively glacial pace in comparison. It just works 10 times better there. In terms of what are other kinds of things that lay out data in similar ways, NoSQL databases have this idea of laying out shards of your database across nodes, and that's how they get to really, really big scale. And a lot of big object stores do very similar things. And then as an alternative approach to doing this that's different than what we do is Crush. And if you're familiar with the Ceph and the Crush papers that have come out from Sage, Crush is really more of a more traditional way to pick a set of data layouts that's a little less mathematically driven and a little more kind of design your failure domains, and then the system can use that map, if you will, in order to decide to lay out data. And so we're different than that. At the bottom, our whole thing is about being content addressable and then solving all the hard problems that come along with content addressability. And so why do we do that? Because we get these really nice benefits from it. We get deduplication, we get data protection, and we get ability to in a much simpler way, build a shared nothing scale-out architecture. Just a little aside, I'm going to talk, I promised I'm not going to do an hour and a half on consistent hashing and content addressability, but I will do a little bit. Just because I think it's so key to our system and it's really core to the way our object store works. So at the top, it really starts with objects, right? And objects have two attributes. They have a key and a value. And this value might be some metadata about what you're talking about, and it's some user data as well. And I consider that all part of the value, right? And so the value is whatever the content of the object is, and the key is how you identify it. Consistent hashing is actually really, really simple. All it does is it takes the key and it maps that key to a database shard via a mathematical function, rather than a metadata server. That's building a map and maintaining a big complex index. And so it's just replace index with math on the key, and that's how you find a shard of the database or a shard of the storage system to actually find something. Content addressability is just a property of the way keys are generated. So instead of the user picking a key, the key is picked mathematically based on usually a hash function that's applied to the object data. It can be a lot of different things, but hash function where you take the object data generates a unique identifier for that particular content. So anytime you run the same data through that function, you're guaranteed the two properties that you have that it's important that this function have are that if you take the same data and you run it through this function, you will end up with the same key. And if you take different data, you'll end up with a different key. Again, it'll always be that same different key. Those are the only strict requirements for content addressability in the function. You want some other properties, and I'll talk about the Exablox flavor of this. And why do we care about consistent hashing and content addressability? I mean, it's like, okay, this is some interesting technology, but why do we really care? Because this is what enables us to eliminate metadata servers, and to make scale out easier. It enables deduplication because this is the signature of your object, and so you actually have now a database of signatures of content, and so you can deduplicate very easily. And it enables end-to-end data integrity because you have a big identifier that uniquely identifies a piece of content. You can always check that content. You can regenerate the identifier because it's just math. And you can always check that your content hasn't become corrupted, because you'll get the same identifier, and if it's different data, you'll get a different one. So it's really easy to check. And so you get end-to-end data integrity.
Now, are objects hashed, or is it subparts of objects?
Right. So now we talk about Exablox style. Right?
All right.
And so that's the high level. This is what anyone that talks about consistent hashing, that's kind of the definition of what they're talking about. And the thing that differentiates the different vendors is their interpretation of what pros and cons they're trading off for each of these things. So when we talk about the Exablox style, in Exablox, I don't actually address it in the slide. So in our file system and in our object store, in the object store layer, there's no such thing as files. Object stores are flat, right? They're just flat things. Our file system takes a file and divides it up into many objects, and it's up to the file system to decide for the workload that it's working with, what's the optimal object size. And there's a couple things it's trading off. It's trading off bigger objects mean more efficient for sequential workloads, but also mean less deduplication, and random I/O performance for the 10 bytes in the middle gets much worse. So it's the file system's job to kind of figure out what's the appropriate object size.
Is the deduplication done at the object level or sub-object level? Or?
We do. So I think from your terminology, it would be the sub-object level. So we're a POSIX file system at the top. So the POSIX file system's job is to turn files into objects. And we turn, in an object store, you'd call a sub-object is really a piece of a bigger one. And so what our file system does is it takes a piece of a big file and finds the best optimal object size for that file in that directory, and that tree of files. And that's what below the object store is when it receives put and get requests, it's operating on these smaller objects, sub-file objects. Does that answer your question?
So let me ask the question one more time.
Okay.
Is the deduplication at the object level, even though you might take a file and separate it into multiple objects, or is the deduplication at the sub-object level? So if I've got a big file with lots of objects, it's actually deduplicating below the object level.
Sub-object level. Sub-file level. It is the latter.
Sub-file level, I understand. Sub-object level,
I'll draw. How about I draw a picture?
Time for the whiteboard.
Please. Time for the whiteboard, yeah. Sorry.
You kept saying sub-file level. I'm saying, okay, that's fine, but you are dividing a file into multiple objects.
Right, so
that's okay.
Here's a file divided up into objects, 01, 02, 03, 04, 05. So each one of these, we generate our hash function on.
So it's at the object level. Deduplication is at the object level.
At the object level, yes.
So that's the third time I've asked that. You've answered it 3 different times. I
think we have a terminology disconnect.
Perhaps.
Right. I think the problem is we have a terminology, and I'm trying to translate from what you might hear a traditional object, like an S3 style object store. If you have an object in S3, it's roughly the same thing as a file. Right. It's something really large in its variable size. Right. What I was trying to contrast to is unlike S3, where it's one file equals one object. For us, we take that file and we turn it into sub-file components. Each one of those represents an object in our object store.
And you're hashing the whole object.
And then we hash at the object level. And we hash at the object level. And that is where we apply dedupe, is at the object level. Okay. And so deduplication is the job of the object store, not of the file system. Right? Okay. And so it happens when we pick a shard of the database, of the object database to drop things into. It's the job of the thing that handles that hard drive in that slot to decide if it already has a copy on that drive, and if so, do the appropriate thing, and if it doesn't, make sure it writes it.
And those sub-object file blocks that are hashed, or sub-object file objects that are hashed, are variable length?
Yes, they are.
So if one grouping is more beneficial to be chunked up in a certain length versus another.
Exactly. So our engineering trade-offs for that have to do with, how much compute power do you have? What do your workloads look like? And what's the optimal object size for the workloads, the compute, the capacity?
From a dedupe standpoint, and being able to maintain less metadata, sometimes larger chunks that dedupe well are better than deduping them all at 4K boundaries or whatever the case may be.
Well, yes.
It depends upon the architecture.
Sure, but then if you have random access, having objects that are large means you've got to do a big read, modify, write. And so then you've got a trade-off there.
Yeah.
And so in general, a smaller object equals better dedupe.
Yeah.
Right.
Yeah.
Of course.
Right? Because
But a larger object gives you better sequential I/O performance.
it may. Unless you're very careful with how you lay out your objects, and I'll actually talk about our strategies there. So our object store is responsible for that laying out that Howard mentioned, and I'll walk down. I'm going to walk top to the bottom through our object store, and you'll actually get to see how that works. So at the top, the data that comes in, we generate our content addressability with a hash function that's a cryptographic hash of the object content. Right? And so we take this sub-file piece, which is a variable size, and we run a cryptographic hash. Today it's SHA-1, tomorrow it might be something different. It gives us a unique identifier for that hash, and it has some really good properties, and we chose it because cryptographic hashes have a really nice property that they give you equal distribution of the hash values, i.e. the keys, across the entire hash space. Which means if I have 10 objects, well, it's statistical, so by the time I get to 1,000 objects, they'll be equally divided all the way around the number line, right, which we just map into a big circle. And so all of the shards will have an equal number of objects, assuming all the shards are the same size. And so that's actually a really nice property. That's why we don't use it for security purposes. We use it for that. And then also it doubles as basically as a checksum. So if you've heard of like the way ZFS does checksumming end to end within its stack, we use our content addressable hash, which is 160 bits versus 64 bits for ZFS.
So something you mentioned, the deduplication domain is based on the objects that are on that object database. Is that what you said?
So at the top of our stack, when the file system's responsible for turning files into objects, so it generates it takes the object data, the subfile data, runs the hash function on it, and then hands the key, that's the key, and the value, which is this data itself, to the object store. So it hands them both. So file system generates the hash, which means that we get top to bottom data integrity, right? As soon as we get the data in, we got a hash of it. So all the way through the stack, the hash and the value travel. So any layer can verify. You can do its extra verification if it needs to. Obviously, there's a performance hit if you do too much verification. And then so it gets to the bottom, that object, that hash is now handed to all of the storage locations that map into where it is.
Yeah. And
then that storage location decides if it needs to store it or not. And so this is actually good because data can bit rot. And if we did a naive implementation of dedupe, we would just do dedupe at the very top level with a global database. But global databases don't scale. And we'd have to have a metadata server that could have the entire database in RAM.
Right,
So this way you get
that's
global,
always data domain problem.
you get global deduplication, but what you do is you push in order to do that, you actually push the responsibility of the implementation of the deduplication to a shard. A shard's responsible for managing.
a shard is effectively a disk drive in this
A
case.
shard's pretty much one-to-one with the drive, yeah, right. And so we'll get there. So storing.
Yeah, but you're not doing the hash
right,
lookup in the processor on the disk drive, are you?
No, we're not.
That would be cool.
That would be cool. It would be. And object drives like Seagate Kinetic and SNIA is working on an object drive specification.
Yeah, you know how well I feel about them.
Yeah, I heard your comments on SNIA before. So yes, the Kinetic guys are trying to do the open source model instead, which I think is going to be
and Western
more effective.
Digital's got their version where you can run your own code on it.
Exactly.
Those look really interesting.
Yep. And this is where we kind of went off.
Ted, sorry,
go ahead.
I just wanted to come back to something I thought I heard you say.
Yeah.
Did you say that the distribution space for the hash values was evenly distributed depending on the size of the pieces that you're hashing?
It's what I said was close. The SHA-1 hashes, or the cryptographic hashes,
Yep.
the values you get from running 1,000 different inputs through them are going to be equally divided across the whole possible range of values. So you won't get bunching.
No, I got that, but I thought you then said for a consistent size.
So what the crux, to figure out how data gets into a particular shard, and this is where different vendors differ, we pick a shard. Our shards are variable sized.
Yeah.
And the size of a shard is dependent on the capacity of the underlying device. So the way to think about it is, if a device is bigger, it will have a bigger piece of the shard, right? It'll have a bigger shard.
Hash space.
and such. So more objects statistically will land on it because of that property of cryptographic hashes is flat.
Yeah.
So if I have twice as big a space, I'll get twice as many objects. So I'll fill up. For every 2 objects that land on me, 1 will land on a smaller drive, which is what you want.
But they're variable size objects.
And they are variable size objects.
So we're getting even.
I'm giving you the the 100,000 foot view.
Okay, great. Sorry, we didn't want an hour and a half on
No,
this.
sorry, I apologize.
Backing off now.
For the 5 to 10,000 foot view, watch the Storage Field Day 3 presentation. Let's not go there again.
Yeah, no. Agreed.
Right. Suffice it to say, it's a lot more complicated than I'm making it sound.
So the object effectively is replicated 3 times across 3 different shards.
Yep. Yeah. We call those ODBs.
Each of those shards could have a different deduplication state depending on what data it received.
Exactly. Yes. That's not a problem. So each shard is responsible for maintaining its own database of objects it's holding on to.
And then when you replicate the data to another Exablox.
Yep. It happens at the next layer up. So that's why replication happens at the snapshot layer. Right? Sorry, site-to-site replication or ring-to-ring replication. Yeah. It happens at the namespace layer. It happens at the layer of files and folders. And what happens is we translate this. We know this list of objects that belongs to a file. We send that list to whoever we want to
hash
have.
Values.
We just send that list of hash values.
Yeah.
And he says, we have APIs through our stack to actually go down and request from an ODB, an object database at the bottom, if it has a copy. Right? We have put, get, do you have it?
Kind of thing.
Kind of questions. And then, but that's just an optimization. We could just send that object to him, and he's just going to deduplicate it, right?
Yeah,
if I say put the same object 10 times, he'll actually store it once. And then the replication is because we've replicated it to 3. And that's what I'm showing here, right, is the adjacent shards. So if this is replica 1 of an object in this shard, replica 2 and 3 will be clockwise around the ring. And so every storage location holds primary copies for the shard and a replica of the shard before it. And so that's how rebalancing works. If if replica 2 goes away, then replica 3 takes over his shard, and he already has copies of those replica 2's objects, right? And then likewise, if this guy goes, he always has, if R3 goes, one of these 2 guys takes over, and they already have copies. And so we limit the amount of data that needs to move in the short term. It's again much more complicated than that. Devil's in the details, and this is where what really differentiates the different.
In a single node cluster that represent disks, and a multi-node cluster that represents disks on different nodes.
Exactly. Yes. Correct. And that's how we guarantee failure domains. In fact, we mix in nodes into the equation as well, so it ends up being more of a hierarchical answer, right? Because we want the ability to lose 2 nodes, so we need to understand which nodes. Essentially, nodes need to be part of the shards, computation as well. So the layout's more complicated than it is at this level.
And you haven't added rack level failure domains yet.
We have not added rack level. We only talk about node and drive today. Right.
Taking remote replication.
Yeah. Sorry.
Right.
Yeah. Right. Yes.
Can you make more replicas?
Yeah.
Can you make 4, 5, 8?
Say it again.
So you're now making 3 replicas, right?
Yes.
Can you make 4, 5, 8?
We can really make any number of replicas. It's tunable in a config file. It's not. It's not even hard coded in the code.
Oh my God! It's a config file.
Yes. Actually, it's in conspiracy. It's an attribute in the conspiracy data.
It's a conspiracy.
In the interest of time, maybe we can jump to the terminal page.
Yeah. Right. So, we already talked about most of this stuff anyway. I'm just going to skip this. And at the very bottom of the stack, and this is the last slide, we've got a fast persistent attribute database, which we store in that internal SSD. If you walked into the lab and saw the open box, we've got an internal SSD. We store essentially, this is where we store the key to where on the journal did we put it. And that enables us to do really fast deduplication with 1/4 of the RAM of everybody else. It's also the key to scalable garbage collection and object iteration across large deployments or large data sets. Essentially, it's append only, so we write in these things called journal pages. We collect objects that are related into a journal page, and so this helps with performance. Later on, when you go back to read, if it's a sequential read, we'll have packed adjacent objects in the file together in the same JPage. So one read will actually, load all the ones you're about to need. And then this is a write anywhere type system. We write wherever the head's closest to on a spinning drive. So it actually maps really well to, in our what we call journal pages are large entities. Again, variable size, but tunable based on the technology of the underlying device. So for shingle drives, we can tune these to be 10 gigabytes, and essentially it works the same way a shingle drive works, where there's a write cursor, and then we write entire journal pages. We don't write sub-journal pages.
So where are you accumulating the journal, in the SSD?
No, so the journal's actually on disk, and the only thing in the SSD is the object ID to which journal page it's on.
Okay, but if I've got a shingle drive, then you've got to be writing smaller than the journal size to
So
it.
we append to a journal page, but if we're going to go back and rewrite it, because we were going to modify an object,
Okay.
then we'll append the new object to the journal page. It's content addressable, so we can't actually modify that object. We'll actually end up with a new object ID. It'll get appended. Eventually, that old object, it may be in this journal page or a full old one, will be garbage.
Right.
And once we've accumulated enough garbage, the garbage collector comes through and then reorganizes pages so that you can think of it as electrons moving or as protons moving, right?
So,
it either moves all the holes, all the garbage into
so you can deal with
pages, or it
shingle
moves all
drives
the
by
other ones that way.
you can deal with shingle drives by matching the journal size to the zone size.
Exactly. Yeah.
Okay.
So that's really, basically we drop both the metadata about the objects as well as the data co-resident onto these journal pages, and it really helps with performance.
If you use the flash drive, replicate it in some way.
We don't replicate the SSD inside, and the reason we don't is because everything on that drive is regeneratable from the disk drive or underlying, or the SSD underlying. The drive we drop the journal on is self-describing. Okay. Essentially, this internal SSD, this attribute database, is an optimization, because spinning drives, you don't want to seek around to find out what's actually on them. And so an ingest, a reconstruction of a failed SSD, is a sequential read of that drive. Updating the database with what it found.
SMR and rebuild. So do you rebuild a journal stripe at a time?
A journal is just a list of objects. It's not a journal like in a. Yeah, no, I understand, but like in a journal in a log structured file system. I have seen people make the mistake of putting SMR drives in a Soho NAS. Oh yeah,
and the drive rebuild takes months because they're trying to do small in-place writes to zones. Yeah, and so the problem there is, if you try to put a traditional file system on a drive like a EXT or a ZFS or a XFS or whatever, it's ugly. It's going to be horrible, because while they are journaled file systems, they're still block. It's just metadata journal. It's not. But they're still block-based. Yeah. They're block-based file systems. We're object-based file system. We don't look at block addresses at all. We only look at journal pages, which are much larger entities. Right. So if I have a drive, and each journal page is self-describing. So we linearly write. So format for us is like a zero I understand
thing,
that
right?
on a normal operation, but if I got a drive fail, then do you?
So reconstruction of that drive.
Yeah.
So reconstruction is also sequential, because we don't care where on the drive the objects land. Right. What we care about is we take the objects that only have 2 replicas left, and we put a third one here. And so this is very different than RAID. If you're in a RAID array, of course, you're going to have the spindles are all in the same place, right? We don't care. Okay. Just as we just lay it out whatever order they arrive at us.
As I tweet my retraction of would be stupid, I want to make sure I got that right.